Hello friends, I welcome you all to the next lecture of the JC eConnect series of online lectures. We are in module 4, Design for Shear. In previous lecture we have discussed about some key points which again I will be briefly repeating, and we have solved one example with 3 categories in it. Let's move on to the further examples in this lecture. So points to focus, I have kept them purposely so that you should not forget them. This is the same as explained in the previous video, where for an rectangular section the shear stress can be calculated directly using the formula 3 by 2 into bracket V divided by B into D. Even this point was already highlighted in the previous video, where for a sagging cable profile we get two components, that is one horizontal and one vertical component, and the shear force is obtained by taking the difference between WL by 2 minus the vertical component of the force. So let's start with today's examples. So first example for the day is, we have a rectangular section of size 150 by 300 which is pre-stressed by a parabolic cable having an eccentricity of 100 mm. Okay, so eccentricity given is 100 mm. Then the eccentricity reduces to 0 at the supports. The span is given as 8 meters. The beam supports a live load of 2 kN per meter, that is the UDL is 2 kN per meter. We have to determine effective force in the cable to balance the dead and live load on the beam, then estimate the principal stresses. Okay, so now the catch in this example is P value is not given to us. Using our basics of PSC, we need to first determine the value of P, that is the pre-stressing force, then go on to calculate the principal stresses. Such examples become tricky or a bit difficult in the exam because you are looking at these examples module wise. This sum comes in the shear module, okay, that is the module 4, and you think that the examples will be related only with calculation of shear force, principal stresses, etc. But in this example, first we need to compute the value of P and further use that value of P to obtain the principal stresses. Let's start with the example. So first calculation is the basic, that is self weight, B into D into density of concrete. We get the self weight of the beam as 1.08 kilonewton per meter. Therefore the total load, okay, the total load will be summation of self weight plus UDL given, which is 2 kilonewton. So we get a total load of 3.08 kilonewton per meter. Eccentricity is given as 100 mm. Now this is the most important thing in this example. We use the concept of load balancing, that is, if P is the effective pre-stressing force, P into E is equal to M. So this part is very important, that is, we are using the basic concept of load balancing. Therefore P into E is equal to M. M is nothing but WL square by 8 for a simply supported beam. Therefore substituting the values, substituting W as 3.08 kilonewton per meter, substituting the length 8 meters in terms of mm, then dividing it by 8, we get P as 24640 Newton or 246.4 kilonewton. Okay, so in the first step we are able to calculate the value of P. In the previous example this value was given. So here we have used a basic concept of load balancing, and in the first step we found the value of P. Many times the students will feel that P is missing or data is not given and they get confused. So I request you all to focus on this point in this example. Now further the example is easy. So let us first calculate the value of theta, which is given by 4E by L, as it is a single jacking end. If nothing is mentioned, always consider it as a single jacking end and move ahead. So when we substitute 4 into E divided by L, we get the value of theta as 1 by 20. If you want, you can calculate 1 by 20 ka value or keep it as it is. Anyhow, it will be a small value only. So now comes your vertical component. Vertical component of the pre-stressing force is given by what? P sine theta, and as theta is very small, sine theta is theta itself. So P into 1 divided by 20, we get the value as 12.32 kilonewton. So now next step, let us find the reaction at the support, that is your support reactions with dead load and dive load, that is WL by 2. When we substitute the value, we find that the support reaction also is 12.32 kilonewton. So this is a unique situation where what is happening is the reaction which is developed at the support 12.32 is completely balanced by the vertical component of the pre-stressing force. Hence, the resulting net shear force at the support is 0. So see these 2 points. Okay, so this becomes very important. Next, horizontal pressure at the support. Now we can find the horizontal pressure directly, that is P divided by area. Okay, we are finding the horizontal pressure here directly using the relationship P, which we have found out, divided by the area of the section. We get the answer as 5.5 Newton per mm square. Therefore, this horizontal pre-stress itself is the principal stress, because there is no shear force existing here. There is no shear force existing means the vertical component of the pre-stress is able to entirely balance the pre-stress shear developed. Hence, V at the support becomes 0 and we only get horizontal pre-stress at the support, which itself is the principal stress. So, two important points. One was in the previous view, and in this view we are getting the important point as V is 0. The horizontal pre-stress at the support is itself the principal stress. We did not go ahead and apply any formulas and find any values. Directly, what is the horizontal pre-stress at the support is itself the principal pre-stress, which is compressive in nature. So I have selected this example specifically so that you will not face any difficulty in solving this. Let's move on to the next example. In this, we have taken a post-tension beam of rectangular cross section 200 by 400. Length is 10 meters. It carries an applied load of 8 kilonewton per meter, which is UDL. Effective pre-stressing force in the cable is 500 kilonewton and cable is parabolic with 0 eccentricity. E is 0. Okay, note down E is 0 at the supports and maximum eccentricity at the center is 140. Okay, so E is 0 at the support and maximum value of E at the center is 140. Now, what we need to compute first is we need to calculate the principal stresses at the support. Second, what will be the magnitude of principal stresses at the support in the absence of pre-stress? Okay, so in the absence of pre-stress, what will be the magnitude of principal stresses at the support? We need to calculate. So remember, this is a post-tension beam. Okay, means the tensioning is done later. So a stage comes where the point B becomes valid. So we need to calculate that value. So let us start. So first we have found out G. Now G is nothing but your self weight. The calculation is given here, that is the area of the section 0.2 into 0.4 multiplied by density of concrete, you get 1.92. Q is nothing but the live load or the applied load, which is 8 kN per meter. Pre-stressing force is given as 500. Eccentricity is 140 and length is 10 meters. Okay, so let's start with the example, solution of the example. So theta calculation remains the same. For E by L, we get the value of theta as 0.056 radians, again which is a small value. Now vertical component P sin theta is nothing but P into theta. We get the vertical component of the shear pre-stressing force as 28 kilonewton. Horizontal component is nothing but P cos theta. Now here just the example is shown. By substituting theta, what happens? Nothing happens, because when theta is small, cos of theta is nearly 1. So we get an answer of 0.998, which is considered as 1 itself. So you can directly take 500 only. Okay, because the horizontal component P cos theta is nothing but P into 1, because when theta is very small, cos of theta is 1. So next, maximum shear at the support due to loads. So maximum shear will be 8, which is the applied UDL, 1.92, which is the self weight, multiplied by the span, which is 10, and as it has 2 supports, divided by 2. It is a simply supported beam. So 49.60 is nothing but the reaction at the supports. Therefore, the net shear at the support is this reaction minus the vertical component of pre-stress, because as we have studied earlier, the vertical component of pre-stress reduces the action of shear at the supports. Therefore, the net shear at the support is 21.6 kilonewton. So now in the next step, let us go to find shear stress. As it's a rectangular section, shear stress tau V, we can use the direct formula 3 by 2 V divided by B into H. So we get the shear stress as 0.405 Newton per mm square. Now these all are repetitive calculations. If you have done the first example properly, here you can move very easily. Now the direct stress, that is Fx. Okay, direct stress means nothing but Fx is what? The given force divided by area, that is 500 divided by 200 into 400. We get the direct stress Fx as 6.25. Now the maximum and minimum principal stresses. There is no vertical pre-stress here, so Fy is 0. Don't get confused between the vertical component of pre-stressing force and vertical pre-stressing force. Okay, because the vertical component comes because your cable is sagging, it is parabolic. So P has a component PV and PH. PV is not the vertical pre-stressing force, please remember this. Hence, as vertical pre-stressing force is not there, Fy is. Therefore, by using the Fx value, we get the maximum compressive stress as 6.275 Newton per mm square, and minimum tensile stress we get it as minus 0.025 Newton per mm square. Now in the next criteria of the problem, what is asked is, if the pre-stressing force is absent, what will happen? So if the pre-stressing force is absent, the reaction which we had got itself remains the vertical shear. There is nothing subtracted from it. The reaction which we had got was 49.60 Newton. So it remains the same, 49.60 kilonewton. So we have to use this directly to find the maximum and minimum principal stresses. But now in this case, maximum and minimum principal stresses are nothing but the shear stress itself, because there is no pre-stressing force acting. So considering this section as pre-stress section itself, we calculate the value of tau V, that is 3 by 2 into bracket V divided by B into D, and we get the answer as 0.93. Okay, so this 0.93 itself is the principal stress, maximum as well as minimum, as there is no pre-stressing force. We have taken a case where it is a post-tension beam just before application of post-tension process. What can be the scenario at the section we want to analyzed. So here it's a pre-stress section itself, but without any pre-stressing force, because pre-stressing force is just to be applied after this stage. Okay, at that stage what will be the stresses we have analyzed in this example. Hope you all are going through the examples properly. If there are any doubts, I request you all to contact me immediately. Thank you. Have a nice day.